Hello, welcome to another module in this massive open online course. So, we are looking at the conditional Gaussian probability density function, and let us continue our discussion. So, one of the important concepts, or you could say principles of linear algebra, is the conditional Gaussian PDF, and we are specifically looking at a scenario where you have two quantities y bar, h bar. These are jointly Gaussian. Typically, we would like to consider a scenario where, for instance, y bar is an observation. So, we have a set of observations and h bar is an unknown to be estimated, an unknown quantity. So, this quantity is to be, this is an unknown quantity that is to be estimated. And we have seen that the conditional mean, that is, we have y bar, or we have this probability density function, conditional probability density function h bar given y bar. This is Gaussian. In fact, the conditional mean, that is what we established last time, if you go back and take a look at it, is that expected value of h bar given y bar, this is what we call as the conditional mean, okay, conditional mean of h bar conditioned on y bar. This has an interesting structure. This is RHY cross covariance of h and y times RY inverse into y bar. This is the conditional mean. Now, in order to determine the PDF, we also have to determine the covariance of h bar given y bar. So, we ask the question, what is, so what is remaining is the covariance, in particular the conditional covariance, the covariance matrix, in particular the conditional covariance. So, we have this denoted by this covariance of h bar given y bar. What is this quantity? Now, to do that, let us start first once again with the covariance of this quantity z bar given y bar, where you remember z bar is something we had defined as h bar minus RHY into RY inverse into y bar. So, we had constructed this vector z bar, remember, to aid us in this derivation. So, z bar equals h bar minus RHY RY inverse into y bar. Now, we ask the question, what is the covariance of this? Now, the other thing that we had seen is that expected value of z bar y bar transpose, this equal to 0, which implies these are uncorrelated, implies z bar comma y bar, these are uncorrelated, and this also implies z bar comma y bar are independent these are independent, right, z bar y bar are independent. You can also say these are independent since they are jointly Gaussian, since they are Gaussian. Okay. And therefore, now what does that mean? And therefore, now this Now, since z bar and y bar these are independent, this essentially implies covariance of z bar given y bar, this is simply equal to the covariance of z bar, because z bar and y bar are independent. So, probability density function of z bar given y bar is simply the probability density function of z bar. Therefore, the covariance of z bar given y bar is simply the covariance of z bar, because z bar and y bar are essentially independent. Now, we simplify this covariance of z bar, this you can derive as covariance. Remember, z bar is a 0 mean random variable. So, covariance of z bar is expected value of z bar transpose, which if you simplify it, use the expression for z bar, this is expected value of you have your h bar minus r h y, h bar minus r h y, r y inverse y bar into h bar minus r h y, r y inverse y bar transpose, which is equal to expected value of let me simplify this, h bar minus r h y, r y inverse y bar into h bar transpose minus r h y, or taking the transpose of this quantity, this becomes y bar transpose, r y inverse transpose is r y inverse, because r y is a symmetric matrix, and r h y transpose is r y h. So, we use the property here that r h y transpose is nothing but r y h. This is something that we had established before. This is easy to see, because r h y is nothing but expected of h y transpose, and r y h is expected of y bar h bar transpose, and these are transpose of each other. Okay. Therefore, now if we simplify this quantity, you will have, this is the expected value of, well, writing it term by term, h bar transpose minus r h y, r y inverse y bar h bar transpose minus h bar y bar transpose times r y inverse into r y h into r y h plus r h y into r y inverse into y bar transpose r y inverse r y h. Okay. And this is equal to, take the expected value of h bar transpose, this is r h minus r h y into r y inverse into expected value of y bar h bar transpose, this is r y h minus expected value of h bar y bar transpose, this is r h y into r y inverse, I am sorry, this has to be r y h subscript h r y h plus you have r h y r y inverse expected value of y bar transpose, this is r y into r y inverse into r y h, and needless to say this r y inverse into r y, this is identity. So, this becomes your, these things cancel. So, this becomes identity, and therefore, you are left with the result that the covariance matrix of z bar given y bar equals the covariance of z bar, which is essentially, since this z bar is 0 mean, this is z bar transpose, this is r h minus, you can see r y inverse r y h minus twice this plus again the same quantity R H y R y inverse R y h, and now if you simplify this, you get this is essentially R h minus R h y R y inverse R y h. So, this is the covariance of z bar. This is the covariance of z bar. This is the covariance of z bar given y bar, which is very interesting, or which is essentially also the covariance of z bar. Now, remember, ultimately we want to ask the question, what is the covariance of h bar given y bar? This is the thing that we set out to derive, and if you look at this, we substitute z bar, we substitute for the vector z bar here, which is z bar equals, remember, h bar minus r h y into r y inverse into y bar. So, this is equal to the covariance of h bar minus r h y r y inverse y bar given y bar. But now look at this, the covariance of, now this quantity given y bar, this quantity is a constant, right, this quantity is a constant given y bar, right. So, given y bar, right, given y bar, given y bar, you have r h y r and y inverse y bar, this quantity becomes constant. And therefore, this is equal to, simply now you are subtracting a constant from h bar. Now, subtracting a constant does not affect the covariance or variance. Therefore, this is also equal to the covariance of h bar given y bar. So, therefore, since subtracting a constant does not affect the covariance, so subtracting constant does not affect constant So, this is equal to the covariance of h bar given y bar. So, what we are saying proved is the covariance of z bar given y bar equals covariance of h bar given y bar, which now you can write as R h minus R h y into R y inverse R y h. This is essential. And therefore, now you can write h bar given y bar, this is Gaussian. Remember, this shows that the PDF is Gaussian or multivariate Gaussian. The mean is R h y R y inverse y bar, this is the conditional mean, and the conditional covariance is R h y R h minus R h y into R y inverse into R y. This is the conditional Gaussian PDF. So, this is the conditional Gaussian PDF of h bar given y bar. This is the conditional Gaussian PDF of h bar given y bar. This is the conditional mean, this is the conditional covariance, this is the conditional mean, this is the conditional covariance. Now, if you look at it, now if you think about it, this is something that is very interesting. This is something that we have already seen. My claim is this is something that we have already seen. If you go all the way back and take a look at this what is known as this principle of this LMMSE estimation, the linear minimum mean squared error estimate. If you go all the way back, let me just refresh your memory a little bit. You go all the way back and you look at this quantity, right. If you look at this quantity, this is something that you should have already seen, which is essentially that this thing, that is, if you look at the LMMSE estimate, this is of x bar given y bar, that's it's essentially the same thing. We have replaced the x by h. This essentially is your LMMSE estimate. Okay. And now if you look at this, you will exactly get the same kind of expression. What you are observing here is that if you denote this by what is known as the MMSE, this quantity is what is known as the MMSE estimate, that is the minimum mean squared error estimate. That is, it can be shown that if you set the estimate, remember h hat is unknown, if you set the estimate of h hat, right. Remember, h bar is an unknown quantity. We are trying to estimate h bar after observing y bar, and therefore, one way to derive this estimate of h bar is to set it as the conditional mean of h bar given y bar, that is, set it as expected value of h bar given y bar, which essentially is the R h y R y inverse y bar, which is R h y into R y inverse into y bar, and which is exactly as the LMMSE estimate. So, which is exactly as the LMMSE estimate. And this quantity here, when h and y bar are jointly Gaussian, this becomes the LMMSE estimate. So, when h bar this is the MMSE estimate, this is the MMSE, that is the minimum mean MMSE. By MMSE I mean this is the minimum mean squared error estimate. Okay. So, this is becomes the MMSE estimate, that is it minimizes, that is, if you ask the quantity what is the estimate h hat such that h hat minus x bar norm square, the mean of that, the mean square error is minimum, that is this MMSE estimate. So, what you see is that the MMSE estimate is equal to the LMMSE estimate when the h bar and y bar are jointly Gaussian, which is what we already see, which the LMMSE estimate is something that we already seen. What we are seeing now is something new, that is the MMSE estimate, and it is much harder to derive, but for the Gaussian the MMSE estimate is equal to the LMMSE estimate, that is the best linear estimate, that is the best linear estimate itself is the best estimate. However, this does not hold for other PDFs. So, something important to note here is for Gaussian, that is for Gaussian, for h bar y bar Gaussian, the best, that is LMMSE, that is the best linear estimate, best linear MMSE estimate equals the best MMSE estimate. However, and this is an important property of the Gaussians, right. This is a very important property for Gaussian random vectors. However, this does not hold for others in general. However, this is a very interesting property. However, the above property does not hold however the above property does not hold in general. This is something very important, that is the best LMMSE estimate need not be the best MMSE estimate. This only holds when it is a Gaussian. Okay. All right, now let us consider what happens when you have zero mean. I think we have already seen this, but we can also consider this once more. What happens when h bar comma y bar or non zero mean? Well, very simple. If when they are non-zero mean, we define these new quantities. Let us say expected value of h bar equal to h mu h bar and expected value of y bar equal, let us say, mu y bar. Then we define these new quantities. We define h tilde equals h bar minus mu bar h. And now observe that expected value of h tilde, this tilde quantities, equals expected value of h bar minus mu h bar, which is equal to 0. Similarly, we define these tilde quantity y tilde equals y bar minus the expected value of y bar, that is mu y bar, and this is also another zero mean quantity. This is another zero mean quantity. Now, we can estimate in terms of this tilde quantities. Now, we say expected value of h tilde transpose, let us say this is equal to, it is still denoted by RH, which is nothing but expected value of, because this is nothing but expected value of RH is now nothing but expected value of mu bar h bar minus mu bar h into h bar minus mu bar h transpose, because the shifting by the mean, that does not affect the covariance. So, covariance of h bar and h tilde will still be the same. Similarly, the covariance of y bar and y tilde, y bar, that is expected value of, sorry, y tilde transpose equals r y equals expected value of y bar minus mu bar y transpose y bar minus mu, I am sorry, y bar minus mu bar y into y bar minus mu y by transpose. And similarly, you have your r h y, that will become expected value of r h tilde y tilde transpose equals r h bar minus mu bar h into y bar minus mu bar y transpose. This is equal to your r h y. And now you put these things together, now you will have the conditional PDF of h tilde given y tilde. This is basically a Gaussian with mean, you will have r h tilde y tilde into r y tilde inverse into y tilde into the conditional covariance, that is r h tilde minus r h tilde y tilde into r y tilde inverse into r y tilde h tilde, which again, if you replace these quantities by their logical equivalents, it is not very difficult to see that this is Gaussian, because r h tilde y tilde is r h y, this is r y inverse and this one becomes y bar minus mu bar y, and this quantity, the other quantity, that is the covariance, becomes R h minus R h y becomes R y inverse into R y h, and this is h tilde given y tilde, but h tilde, remember what is h tilde? H tilde is simply your h bar minus mu bar h conditioned on y bar minus mu bar y. This has this PDF. So, you are simply subtracting, which means h bar, to get the PDF of h bar, all you have to do, or h bar given y bar minus mu y bar, that is y bar minus mu y bar, or h bar given simply y bar, because y bar and y bar minus mu bar, that is PDF of h bar given y bar is the same as the PDF of h bar given y bar minus mu y bar, because these are y bar and y bar minus mu y bar simply differ by the shift. So, this becomes now all you have to do is you have to add the mean to this. So, h bar minus mu h bar as this mean. So, h bar will have the mean R y inverse y bar minus mu bar y plus mu bar h, and the covariance will not, the covariance does not remain unchanged, does not change, because remember, simply shifting by the mean or shifting by a mean does not affect, and this is the final expression for the conditional Gaussian PDF, and which is very useful, and as I said, arises, this is the expression for the conditional Gaussian PDF, which is very useful and arises very frequently. For instance, arises in machine learning, data analytics, signal processing, communication, it is there everywhere, and the principle, and this, remember, I already told you, relates to the principle of MMSE estimation, the minimum mean squared error estimation. So, this has a lot of use in that sense. All right. So, that is wonderful. So, I think we have covered this way of, I hope all of you have been able to appreciate and completely understand this concept of the conditional probability Gaussian probability density function, that is when h bar and y bar are jointly Gaussian random vectors. Given y bar, what is the conditional PDF of h bar, and that then determines what is the estimate, MMSE estimate of h bar given y bar, which is nothing but the conditional expectation of h bar given y bar. All right. So, let us stop here and we will continue with subsequent modules. Thank you very much.